Okay, so our next topic that we're going to talk about is the meridional overturning circulation. We've spent an awful lot of time talking about gyres, which are kind of the horizontal circulation. The meridional overturning circulation is an overturning circulation. So it tends to go this way, top over bottom, top over bottom, top over bottom. So it's overturning in that sense, and it's meridional, and then the primary interest is the north-south motions in those surface and deep waters. Wunsch discusses this in great detail in chapter 9, which is a great place to go look. What we're going to talk about here is particularly how the overturning differs from the thermohaline circulation. It's kind of two different names. They mean something very different, though. It is a more modern take that calling it the meridional overturning circulation, or the MOC, or the AMOC for the Atlantic meridional overturning circulation, is much more scientifically precise for reasons we'll get to. We'll talk about how the surface properties of this flow affect water masses, and we'll talk about how mass and energy transports are estimated, and finally we'll talk about the primary patterns of overturning. And this is sometimes called the conveyor belt, which is also not a very good name. All right, so we talked an awful lot about sphere drift transport and how it has to close in the west versus the east. It has a western boundary current, which essentially gets new dynamics because it's a drag-driven thing, and then the interior is constrained by the surface winds. And if we go out to the real world and try and draw all the gyres, there's a lot of these horizontal circulations in all the ocean basins. And then there's the ACC, which we're going to talk about next time, because it involves both a horizontal circulation and an overturning circulation at the same time. Fun. Okay. But does the wind do everything? We've learned to associate those features with wind-driven Ekman convergences and divergences and the sphere drift transport that predicts the interior flow. What about heating and cooling? What does that do? What about freshwater and salinity? What does that do? What about the turbulent mixing? How does that come into a way? It's like turbulent mixing, we haven't really touched on it very much except to say that it works in the Ekman layer, a little bit in the upwelling zones, but what about turbulent mixing down in the interior of the ocean or down at the bottom of the ocean? How does that work? So all of these affect the baroclinic flow, and maybe they lead to overturning or mixing or something. So the theory of the driving forces behind the overturning is a little complex, but we're going to try and touch on a few of these points by thinking about it from the perspective of water mass analysis. So if we look in the side of those ocean basins, this is a beautiful schematic which has been drawn over and over again. Started after Arnold Gordon's 1986 paper. You'll find lots and lots of versions of this. But here we see, so this is a hub and spoke ocean. So here's the Pacific, here's the Atlantic, here's the Indian, here's the Indonesian through flow that goes from the Pacific in to the Indian. And here's the Bering Strait transport coming out of the Pacific through the Arctic, which isn't shown, and then back in the Atlantic. But most of the action here is in the ACC, where all these different currents are getting linked together, and in the convection around Antarctica, which is forming this deep Antarctic bottom water, which goes out and fills all the different basins. The deep waters in between, in the Indian and Pacific, are basically mixtures of Antarctic bottom water and the water from above. And then the mode water is formed at the surface of both of those oceans and comes back in a different direction. In the Atlantic, we also have convection up here in the North Atlantic, forming the North Atlantic deep water, which heads back this way, mixing with Antarctic bottom water on the way, and kind of riding on top of the Antarctic bottom water. If we think of it in this kind of combined way, we can still draw these currents. Notice that most of them are over on the west. You know, the Atlantic, so here we have the Gulf Stream coming up this way and then sinking in the Labrador and Normandy Seas and coming back this way. Here's the Antarctic bottom water coming out even deeper. Here's the Antarctic bottom water coming out even deeper. And then there's a whole lot going on, and these are using colors to indicate depth, which is a little funny. They don't have relative transports here, and they don't have the gyres cleanly drawn on top in every basin in the right way. So this is still a significant underestimation of the complexity of the flow that we're thinking about. If we just look at the salinity and temperature, so here's, let me get this right. Here, the bottom is oxygen, this is salinity is B, and temperature on the top. We see the stratification that we expect, but we also can recognize water masses like the North Atlantic deep water. This is just the Atlantic, which is anomalously salty because of the Mediterranean water. It's a wedge of water that comes in this direction. The Antarctic bottom water is down here. It's fresher and it's colder. And then oxygen is a really useful tracer because oxygen gets consumed and it gets recharged when it's at the surface. So high oxygen indicates young water, water that was recently at the surface. So you can see the North Atlantic deep water is relatively young in terms of oxygen compared to the Antarctic bottom water. Yeah. Well, the Antarctic bottom water underneath it, but not the Antarctic bottom water over here near that it's just formed. In an even more schematic way, we might think of something like this, where we have northern sinking and southern sinking and a picnic line, and there's upwelling through it. This is a nice conceptual model, which we'll come back to as we think about the southern side of this. But this is the way that balancing all these different transports in different places is how we actually set the depth of the picnic line, not the variations we've been talking about with convergences and divergences and gyres, but like how deep is the picnic line overall? You can take these schematic diagrams and put numbers on them to try and get the mass transport and spherodraps for the global overturning circulation and the heat transport in petawatts like this, and the direction that they're going in. This is nice. You can, if you make a transect through 24 north or 26 north, I guess, you could compare it to rapid. All kinds of stuff like this. And we still have in mind this convergence at the surface, this formation of water at the surface and then cruising along isopycnals beneath. What we're trying to do, however, is just to think about all the different layering flows that go below. So in the sense that this is an overturning circulation, it's overturning because there's different directions of flow going in different depths. And it's meridional because we're really always plotting the south on one side and north on the other. So we're thinking about the meridional. In the zonal direction, you might be thinking, how do we get to spherodraps if we're not integrating that direction? This is also integrated in the zonal direction when we put these numbers on it. So this is 19 spherodraps, which is 18 across the Atlantic and 1 across the Pacific, as we integrate all the way in the east to west direction around the whole Earth. So this is like the collapse after integrating all the east and west directions, a zonal integral into transports in both petawatts and mass. I just like I like the mixed layer, so I like watching the mixed layer cruise around. The mixed layer is an important part of this, and there's an aspect of the mixed layer called Stommel's demon, which is where the properties at depth, that is, those subducted properties, are set by the coldest wintertime conditions and the deepest of the deepest mixed layer. That's because basically after the mixed layer gets deep, it doesn't retract and suck the same water back up. It just gets capped off by warmer water. So that deepest water is left to move on downward into the interior of the ocean. And so when we think back to, like, I don't even know, second class, when we talked about the heat transport, meridional heat transport, the southward energy transport, northward energy transport from the top of atmosphere radiation here, and then the atmosphere in this dotted line and the ocean being the difference. This is to balance the top of atmosphere net radiation. Remember, we have incoming radiation across the tropics, outgoing radiation across the poles. If you integrate overall, you get close to zero. Not exactly zero under global warming, but it would normally be zero. This heat transport is needed to take the excess heat that arrives at near the equator and move it towards the poles. And here's the ocean component in the total in black, Pacific, Atlantic, and Indian. And you can see that that funny Atlantic circulation being positive here is partly because of the Atlantic overturning circulation. That's because of this sinking deep water at the North Atlantic that comes back as the North Atlantic deep water. So these energy diagrams are directly related to this complex set of flows over here in terms of petawatts. And if you add these up, you get numbers that are pretty similar to what's in there. Or you could try and directly estimate by the ocean first. I should have said this is the residual of what the atmosphere doesn't do is how this is figured out. Or you could do it by measuring in the ocean first, as Wunsch talks about. And there's a whole lot of seasonality in this signal. So you want to be a little bit careful about thinking about wintertime hemispheres and summertime hemispheres if you want to do this carefully. And the fresh water kind of oscillates up and down. We know that this has to do with the patterns of global precipitation. We already talked about this being rainy at the equator, dry in the subtropics, and then there'd be transport from one to the other to try and balance that out. This also has to do largely with the meridional overturning circulation, except now the mass transport part of it rather than the temperature transport part of it. So the mass transport is bringing the fresh water, but also the salt. And then the evaporation is removing the fresh water. So it's just like we did in budgets way back when for the estuaries, think about the salts and volume budgets. The same kind of process is going on now on a global scale. Okay, thermohaline circulation. So why is it not called the thermohaline circulation anymore? It kind of went out of fashion, largely due to Carl Wunsch's efforts on this front. There are 7 different and inconsistent definitions of the thermohaline circulation. It's the circulation of mass, heat, and salt. Okay, that's sort of consistent with what we've been talking about. The abyssal circulation, just the bottom part of that overturning. The meridional overturning circulation of mass, or the global conveyor, which is partly meridional and partly gyres. Circulation driven by surface buoyancy forcing, circulation driven by density and or pressure differences in the deep ocean, and the net export by the North Atlantic of a chemical substance such as protactinium. All of those are called the thermohaline circulation, but really the name itself really means temperature and salt circulation. And people tend to think of it as the circulation driven by temperature differences and salt differences. We have to be really careful about what we mean by driven by. Does that mean just cold water going from the cold place to the warm place, or does that mean garnering energy from that cold and warm, cooling and warming of the circulation? So here are some other slides from Gökhan Denebashoglu talking about similar aspects, but the thermohaline circulation indicates a driving mechanism, which is what I was just saying. But the density differences are primarily caused by surface fluxes of heat and fresh water and subsequent interior mixing. So the density distribution itself is affected by the currents and associated mixing. So thermohaline and wind-driven currents interact with each other, and they can't be truly separated. So when you say, it's not like you say the wind-driven circulation and the thermohaline circulation, and they're separate. They're intimately linked. So if you say it's driven by the winds or you say it's driven by thermohaline, you can't, because the response to the winds depends on the thermocline, and the thermocline depends on some of the transports like the warm Gulf Stream and cooler interior flow in the North Atlantic gyre. Okay, so meridional overturning circulation as opposed to thermohaline circulation is really a mathematical term, because we can just integrate the transport, the northwest transport, in the zonal direction and with depth, and make ourselves a stream function. This stream function is a volumetric stream function. So if we take its derivative with respect to z, we get the vdx. If we take the derivative with respect to x, we get the vdz. And so this is giving us that overturning part of the circulation in units of spherodraps. It includes the wind-driven circulation, but since the wind-driven circulation is going this way, at least the gyre part of it is, it cancels itself out to a large degree, with an exception that we'll see in a minute. you can think about this more fundamentally, like, is that really a stream function? And what is a stream function? Well, a stream function is something normally that you take the curl of to get a velocity field. And so what we really mean by this meridional overturning stream function is not this stream function, but the integral of that stream function in an additional direction. So this stream function has the units of velocity times length. This stream function has the units of velocity times length squared. So we've got another integral going in this meridional overturning stream function. Velocity times length squared, of course, is meters cubed per second, so spherodraps. We can make what's called the barotropic stream function. So we take the stream function having to do with the gyre, circulation around the vertical axis, take that stream function and integrate it with depth to get a depth integrated volume transport of the gyre. That's called the barotropic stream function. And it's related to the z integral of u and the z integral of v like this. This is a useful thing to think about as well. It's closely related to the meridional overturning circulation, and it's a transport stream function. It is one that is measured in spherodraps. And when you take its derivatives, you get the depth integrated transport. The meridional transport, in fact, is not the z component of the stream function, it's the x component, the component in the zonal direction about which the overturning, meridional overturning is occurring. So if we think about that for a second, we want to integrate that one along its axis, so along the zonal direction. When we do that, we get something that has the units of spherodraps. If we take its derivative with z, we get the x integrated meridional velocity. If we take its direct derivative with respect to y, we get the vertical velocity x integrated. Cool. This is the meridional overturning circulation. This is the meridional overturning transport stream function. What does it look like? It looks like this. You see some stuff up here that's like the wind-driven stuff, like Ekman and things. You see a big overturning cell here in the Southern Ocean. You see a big overturning cell over here, the North Atlantic deep water in the North Atlantic. And you see another overturning cell over here in the Antarctic bottom water. These arrows help you remember which sign is going to which direction. And these are circulations, so they're overturning patterns, just like we saw thinking about the pressure contours in the geostrophic flow. So here in just the Atlantic, you can see most of this overturning up here is actually an Atlantic signature of the North Atlantic deep water and the Antarctic bottom water coming in underneath. The North Atlantic deep water's got about 20 spherodraps or so of flow. The Antarctic bottom water, at least here, is not so much. I think it's in units of 4, so it's about 4 spherodraps or so of Antarctic bottom water transport. Is convection part of it? Well, yes, it is, in the sense that cold stuff is dropping in depth. So here we're looking in potential temperature. You see cold anomalies going all the way up to the surface. You see salinity anomalies going up to the surface. These are signatures of convective activity. A convective chimney west of the Maud Rise in the open Southern Ocean. So once that convective chimney comes down, it's linking these density surfaces from the surface down. So that is part of the meridional overturning circulation. Once something is convected, though, how does it get back to the surface? It doesn't convect back up. It doesn't warm. I mean, aside from geothermal heating, which is very weak, it has to mix its way back to the surface. So you get a convection and then mixing kind of system being the way that things are moving around. One interesting way to think about that is to, rather than plotting the vertical axis in depth, to plot the vertical axis in the density of the fluid. So once it's gotten out of the mixed layer and down into the potential density, once it's gotten down into the deep ocean, it doesn't change its potential density much. So this North Atlantic deep water, while it's convecting, it's doing something interesting, and then it cruises along on the same depth, but also the same density surface. So here it is in density latitude space. It's changing its density. It's getting less dense, less dense, less dense. Oh, sorry, this is the Southern Hemisphere one. Here we're seeing this is this one. this is this one, and this is this one. So look at the red one. The red one is going this direction, down and back up, this direction, down and back up. So it's getting more and more dense until it sinks at a particular density, and then it completes its circuit. It's got to mix its way back up to get to here. So I'm emphasizing it's mixing because it's changing its potential density, which means that it's being mixed. Whereas when it's transiting here, it's at the surface, it's actually in contact with the air sea fluxes, so it can be cooled by cold air above or by long wave radiation out. Then it convects back down, sinks, moves around. So looking at these two together is a nice way to think about the density transformations that are implied by these different circulations. Here's the same kind of schematics, just showing the echo version from Wunsch. And I believe I've given you code to calculate these if you wanted to look at these and echo for your paper number 4. What is this wind-driven overturning stuff? Well, we talked about it before a little bit. It's really when you have the Ekman pumping, you have this convergence and then it goes down below, it gets heated and comes back up. So we have these lenses of the subtropical gyres, and because the Ekman flow at the surface is not exactly canceled by the flow because it's at a different depth, we tend to have these little overturning circulations that are at the top. The most important one is called the subtropical cell, which goes like this, and it really is an Ekman transport like this. There's no real gyre part, there's no independent gyre part to it, and it goes from the 0 wind stress curl to the 0 wind stress curl line. And if we go back and look, those are really what we're seeing here. It's not going all the way up to the 40s of where the 0 wind stress curl line is. It's going to where the 0 wind stress line is, and then looping back. So that's what these little wind-driven cells are. Okay, so once the water gets down to the bottom, how does it spread out? Does it go like just mix? Does it do something else? There's actually a whole separate circulation theory for what's called the abyssal circulation theory that was put together by Stommel, same Stommel, together with Alan Fowler. So the Stommel-Ahrens-Fowler experiment, they did it first in a lab tank to see how it would work. Their idea was that they would put some stresses, they have a rotating tank, and then they would suck fluid in and out in different places. And they get so this is fluid only in a sector of the tank. So here we have the north end and we have the south end, and they would be able to suck fluid in and out. There was no wind stress applied to this and no bottom stress, just sources and sinks of fluid. You might expect, actually, the way that this would work is there'd be a localized mass source, like where the convection comes down, and then there's uniform upwelling everywhere through the thermocline everywhere else, and no flow through the bottom. So we might have a bottom Ekman layer. Cool. This uniform upwelling is going to be stretching our vortices. This localized mass source is going to be squashing our vortices. So we have the same vorticity balance that we had in the gyre style dynamics, except now we have localized sources and sinks, localized sources of mass, and then sinks that are distributed in a kind of inverse way. So it's not going to look like the wind patterns anymore. It's going to look like some other kind of circulation, and it potentially has a bottom Ekman layer if it needs it. There was a lot of discussion about whether there would be diffusion and convective parts. Vallis's book is a good place to get to it. It doesn't actually do a great job of explaining the thermocline, but it does do a pretty good job of explaining the upwelling as you're diffusing heat down, upwelling up. There's mixing here and convection on the sides. So this is part of this meridional overturning. Okay, so let's see what happens if you have a source here and then uniform upwelling everywhere else. Uniform upwelling is going to be stretching. That means we want to go poleward. everywhere from the sphere flow. Oh, wow. That means that what ends up happening is we have to go from the flow everywhere in the interior is headed toward the source, which is super weird. The way we get out of that conundrum is that we add a western boundary current. The western boundary current will have an active bottom Ekman layer, and so it'll be able to flow any direction it needs to close the rest of the mass budgets. So the source up here first flows actively in a western boundary current down to the bottom where it spreads out and then returns back toward the source as a wide sphere drip-like flow. If you put the source down here, you get almost the same circulation pattern, except now the western boundary current is returning all of this fluid, but doesn't include that source. If you put a negative source here, a sink, you can actually reverse the direction to go this way. If you put a sink here and a source here, you just get a western boundary current and no interior flow. If you put a source here and a sink here, you only get a western boundary flow that you get east-west flow that connects to the western boundary flow, and the same here. These are different configurations of sources and sinks to show that the abyssal flow is really going to be quite different than the surface flows. I won't talk too much about this, but there's basically an analogy between the rotating tank, wind-driven flow, and an abyssal flow that you can make, talking about potential vorticity and the wind stress curl, upwelling mass loss, localized mass source, etc. Okay, so the Stommel-Ahrens flow is typically poleward in the interior with deficits made up by the western boundary currents. That's the basic gist of how this model works. So what do you expect for a realistic environment? Here's what we might expect to see for the North Atlantic. We'd see maybe some recirculation, some flow like this. And this is kind of what models do. This is a nice flow, goes along the western boundary current and then flows back in the interior, back up towards the source. This is showing only the 1,500 meter depth. So this is kind of below the picnic line, and so below the gyre flows, just showing this convection up here and where it goes. This is a deep western boundary current. If you look at oxygen at 2,500 meters from observations, you see that there's high oxygen here and low oxygen here. So if you were to imagine this flow carrying oxygen with it and the oxygen being depleted, this water is younger, this water is older, just as you'd expect from that kind of broad circulation pattern. This one, let's just skip. Okay, so we can also see there's some complexity coming from exchanges with the ACC, lots of weird other deep western boundary currents. Here's a deep western boundary current in the Pacific as well. Lots of things to think about. And here's the oxygen at 4,000 meters, which now is showing high oxygen all around the ACC, and then lower as we go northward. So the Antarctic bottom water, the youngest Antarctic bottom water, is connected to this flow pattern, whereas the older Antarctic bottom water, which is the oldest water on Earth, has low oxygen levels out through at least this is the Pacific, but also the Atlantic, if you could see it. So this doesn't have the pattern of the surface pressures, and we didn't zoom in enough at this 1,507 meter decibars to see the geostrophic flow that is part of this circulation. This is showing the arrows. We could have tried to get the geostrophic flow out of that. One really interesting, not new discovery, but important factor bringing together our talk about waves and instabilities or eddies and the deep circulation is, if you actually carefully analyze what happens with those deep trajectories, there are many more eddying trajectories than there is a deep western boundary current. So this oxygen is not showing you a nice tight western boundary current. It's kind of showing you a big diffuse thing. And that's because there's so many eddies down here that mean circulation is kind of overwhelmed by the lateral transport of eddies. And so the Stommel-Ahrens theory, Stommel-Ahrens-Fowler theory is deficit in that it does not have eddies. eddies are really important to the abyssal circulation in a way that we now appreciate much more than we used to. And so if you look for oxygen, you look for anthropogenic warming of those water masses, you look for bottom velocity predictions, you have to actually think about the eddying contribution quite a bit. This is a really nice paper to look at from Science 2010. All right, so last questions. Are the deep flows geostrophic or not? How are they driven? And what causes them to vary? Well, one way to think about this is to think about what the sources of energy are. This is the energy budget coming from ballast, which I won't dwell on, but here's the essence of how this works for the atmosphere. You're cooling everywhere as you're releasing long wave radiation back to space, and most of the surface heating is actually near the surface. So the sun comes in and heats the bottom, and then it convects. Heating below and cooling above is a source of energy. So Z times Q hat is the heating, Z is the height. So here when Z is big, we are cooling, that's negative. When Z is small, we are heating, that's positive. So put them together, positive and lower Z's. So we tend to have a negative number overall, which means that this actually produces energy for the rest of the circulation. So the rate of change of kinetic energy and potential energy is minus ZQ minus the dissipation. And if minus ZQ is less than 0, then you can actually make this end up being positive for a while, which creates the energy. So the way that we say this is that the atmosphere is a heat engine. It is an engine for converting thermal energy into mechanical energy. What if we do the same mental game on the oceans? We're cooling and heating all at the surface, all at Z equals 0, more or less. If Z times Q hat, Z equals 0, is just equal to 0 everywhere, because Z is equal to 0 all along the surface, that means that you do not have any energy generated from this heating and cooling pattern. There is nothing to drive dissipation. So if you start if you take a moving ocean and only heat it and only force it with heating and cooling at the surface, you very quickly damp out to no circulation or almost no circulation. That's a very surprising result, because it tells you that the thermohaline circulation, the thing that's driven by heating and cooling, has no energy in it. It's only through its combination together with mixing and wind-driven components that allow this cooling and heating pattern to extend to greater depths and to draw energy from what's going on. So if you think of the convection, that's clearly drawing energy because it's dense at the surface, it has potential energy, and then it drops. So it's converting potential energy to kinetic energy as it drops. But then when it goes back up, it's extracting energy from the mixing to lift it back up. So dropping down, you get from potential energy to kinetic. Then you have to add in potential energy, typically through tidal mixing or bottom boundary layer mixing or something like that, to elevate those waters back up to the surface. These are some schematics of the kind of patterns you get if you are heating and cooling at different levels. So if you're cooling at the surface and heating at the bottom, you get a very strong circulation between the two, like this. If you're warming at the top and cooling at the bottom, you just get stratification, not a whole lot of circulation. You just build up cold stuff at the bottom and warm stuff on the top. If you put them equal, you get a relatively weak circulation and a kind of tilting thermocline between the two. So this comes into estimating the energy circulation of the entire ocean, which is a topic that's much larger than what we want to talk about today. But the point is that you do not put the thermohaline circulation in as a very strong forcing. In fact, in this Wunsch and Ferrari paper, they have it as 0, the amount of energy brought in from heating and cooling at the surface. Okay, is the overturning circulation likely to change? It's extremely nonlinear. It couples both the buoyancy and the convection. The energetics constrain the circulation strength, but is it possible that more than one configuration is allowed? That's not actually disallowed from energy constraints. The Stommel Box Model, Stommel again, he shows a simple box model which has a nonlinear behavior that allows it to have multiple solutions. This is the values of the AMOC in the upper panel and the maximum depth of the AMOC in the lower panel. I don't know why I put this in this, but here's the idea of the Stommel Box Model. You have two reservoirs, each of which are being restored towards a temperature and salinity, this is cold in temperature and fresh. This is warm and salty. So this end is like the north. This is like the north end. This is like the south end. And if you make it denser over here, then over there, it'll flow this way. If you make it denser over here, then over there, it'll flow this way. And so there's this overflow and a capillary, which means that you're basically letting it be a pressure-driven flow at the bottom from one to the other. You will notice this is not a geostrophic flow. It does not flow from perpendicular to the pressure gradient flow. It's flowing from high pressure to low pressure. So this is an ageostrophic circulation in essence, this overturning component. If we were to study this in the real world, you actually could drive this with geostrophic flows, or even more precisely with eddies that were tending to try and work against that pressure gradient, but each of them having their own geostrophic transport. Okay, but you put this system together and you set this temperature T star and you set the S star, and it turns out that this system can have multiple equilibria. What do I mean? It's a little complicated to explain this figure. This is one aspect of the solution, and this diagonal line is another aspect of the solution. This A, this one A, this one B, and this one C are for different parameters of the problem. Parameters like how strong T star and S star are, and other things like the ratio of diffusivity to viscosity and stuff like that, that all comes into this game. Or sorry, thermal diffusivity to salt diffusivity that come into this game. And the only important thing to notice is that, so these are funny things because it's a nonlinear model, and you get a solution at each intersection of this diagonal line and these other ones. So for condition A, we can get one solution here, one solution here, and one solution here. This solution is the thermal mode, which looks like today's circulation, cold water sinking and rising back up at the equator. There's a haline mode, which goes the opposite direction, or at least a much weaker version of, or it actually does go the opposite direction. Here's the overturning strength and stream function. So it has the opposite sign of stream function. So this one is actually salt water sinking at the equator, popping back up as fresh water at the northern end. Very odd. If we now look at B, we see that we don't have, and this middle mode is a circulation in between the other two. It turns out this one is always unstable to perturbation. So if you were at this one, it would tend to drift either into the thermal mode or the haline mode. This A also, so B also has, looks like three intersections, but it kisses on this one. So the unstable mode and the thermal mode have merged. And if you raise just a little bit more up above B, you would have only the haline mode. By contrast, C has only the thermal mode. So now if you imagine climate change shifting you back and forth between A and B and C, you might ride back and forth, jumping among these different intersections as they changed. And so you might start on the thermal mode like we are now, and then be forced onto the haline mode because you get out to condition B or beyond, where only the haline mode exists. And now if you reverse the forcing, you actually would stay over here until you crossed over this unstable mode to go back to the thermal mode. So it turns out that this suggests that there should be irreversibility and potentially multiple modes for the same forcing for the overturning circulation. It's not quite as clear if realistic models rather than the simple box model have this system, but this is definitely something that people worry about. And this is in fact why the day after tomorrow, which we already talked about, whether the MOC can shut down, and this is a whole set of questions. The IPCC spends a lot of time thinking about whether the MOC will shut down, and it was deemed that it is very likely that the MOC will decline in the most recent special report throughout the 21st century. Sudden shutdown is, I can't remember if it's unlikely, or I think unlikely was what they used, that level of certainty. Sorry, I don't know why that figures in there. Anyway, we'd already talked about this Bryden set of studies where Bryden went out and measured the Gulf Stream and the overturning circulation of the Gulf Stream a few times, and then projected that it was getting weaker. But we now, if we, here's the table, but here are the heat transports over from different estimates at 25 north, and you see that there's a whole lot more variability than this actually implies. And so we have talked about this decline here actually should probably be embedded in a much larger set of variability. This is just showing the annual variability versus this. But if we jump onto rapid looks like this, extremely highly variable. And here's ECHO's monthly mean transport as well. So you could redo something like Bryden's series, at least over the years that are, these 3 years that are included within ECHO, and see what you get. And you could make other samples that were from slightly different years and see whether you get a decline or not. This decline here at the end does not persist. Okay. There are some paleoclimate proxies and indirect proxies, like this paper from Stefan Rahmstorf, where they use a paleoclimate proxy method to try and infer that this cold hole, or sometimes called cooling, the warming hole, this part of the North Atlantic does not heat as rapidly as the rest of the North Atlantic under global warming, and that's thought to be an indicator that the cold water that should be sinking is actually not, and so it's like a changing AMOC conditions, meridional overturning circulation conditions, are leading to this cold hole. This is the record that they built, but it's quite this is not agreed upon as being a very accurate method by all the people who observe. And when you get up here into the part that's observed by rapid, this greatly underpredicts the variability. So this method, we don't know how well it works, but something like this is what we need if we want to construct the AMOC going back before the time of rapid, because the Bryden measurements are not good enough in time. Okay, so the MOC involves meridional transport of surface, warm, fresh waters, and deeper, colder, saltier waters. These water masses are formed at the surface and then subducted, consistent or convected. Consistent water properties reveal very slow interior mixing. Unlike the atmosphere, the MOC is not a heat engine. It is driven by other things like mixing. It's getting its energy from something else, not from the heating and cooling of the surface. It's driven energetically mostly by winds and tides, but it transports heat and fresh water, and it would affect the climate if it varies. It's not necessarily distinct from the wind-driven cells, that is, particularly the subtropical cells, part of the gyres. All right, that's the ACC and the MOC. Thanks.